Hi, I'm Jason, and I will be presenting a little bit of theory behind the fundamentals of Poisson Statistics, and also an investigation that we did into background gamma radiation. So let's start with the fundamentals of statistics. Random variables. What does it mean for something to be random? Any ideas?
It means you can't know what the next measurement is going to be based on what the present one was.
Okay.
Is that right?
Unpredictability. So that's one way to define random. I figured that I'd ask the internet. I see the computer has a sense of humor. So this is clearly not what we mean by random. When you say, I want a random number, and you always get 4 back. This is not what we mean by random. It's not a very useful theory if all of the numbers or all of the unknown numbers in the theory have to be exactly 4. So that's not what we mean. So I asked the internet again, a source that we all know and love and maybe trust too much. I asked Wikipedia. Wikipedia says that a random variable is a function from a probability space to a measurable space, typically the real numbers. There are some big words in there: function, probability space, measurable space. I guess we all know what a function is, though. So I asked Wikipedia what a probability space was, and, well, yikes. It was a very long explanation, and I don't think we need an explanation nearly that long to get the basics of statistics. So let's try again. What does it mean for something to be random? And I see the computer is being snarky. But why do we care about what it means for something to be random? Any ideas?
Because humans are terribly unpredictable beasts.
Okay. So again, I hear unpredictability. I think that's part of it. The answer that I think is that we want to be able to talk quantitatively about the relationship between measurements and the theory. We want to be able to know how far we are off from what the theory predicts. Because maybe there are some non-deterministic theories and we want to know how bad it is, or like what we should expect when from those theories. And even with deterministic theories, we usually won't get exactly what the theory says. Maybe we'll measure neutrinos going slightly more than the speed of light. Maybe we'll measure that the speed of light is not constant in a vacuum, and we want to know how bad it is that we got these measurements. And for this, we need random variables. So now that we know why we want random variables, now maybe we can get a better answer to the question of what does it mean for something to be random. And it turns out, I think, that all you need, basically, is the law of large numbers. And the law of large numbers says that the average of any series of identical, statistically independent random variables almost always converges to the true mean. And almost always is a weird word to have in there, a weird phrase. So if you want to know what it means, there's two statements. There's the weak law of large numbers, which says that as you take more and more measurements, the probability that you will get at least epsilon away from the mean when you average them is 0. And there's a strong statement that says the probability that your series of measurements converges to the true mean is 1. And if you want later, you can ask me about how these are different from just asserting that it always converges to the true mean, because they are slightly different. But we don't really care about the details of what it means to almost always converge. It suffices to say that for all practical purposes, any series of measurements that we take, or any subseries of those measurements, almost any subseries of those measurements, when you average them, they'll converge to the underlying parameter that you look at. And why is it enough? Why is the law of large numbers enough? The answer is because everything is a random variable. So in particular, if you're making a series of measurements, you can make a new measurement that is, say, the proportion of those measurements that comes out to be a certain value. And then this must converge to the true value of that underlying parameter. And so having the means converge is sufficient to make it so that the entire probability distribution has to converge to the true underlying probability distribution in the limit. Okay, so now that we know what we know about basic randomness, now we can talk about some simple distributions. So I think the simplest distribution is the binomial distribution. And this arises whenever you consider an event with two outcomes. Something like looking at a light and saying, is it on or off? Or flipping a coin, things like that. And if you make a number of statistically independent measurements of the same event that has two outcomes, which we'll call success and failure, you get this formula where P is the probability of success and N is the number of times that you measure. And so why this formula should make sense is here you have N choose X, that's the number of different ways to order X successes, times the probability that you get a success in each of those X slots. And Q is 1 minus P, it's the probability that you'll get a failure, and that's the probability of getting N minus X failures in the other slots. And if you plot the binomial distribution, you get something like this. Notice that it's discrete, that it's roughly symmetric in a small region, but overall it's not symmetric. So consider the limit where P is much, much less than 1, and the mean NP is fixed. And in this limit, you get the Poisson distribution. It has this formula, and the derivation is mostly straightforward. It's in probably most intro statistics textbooks. For example, it's in Bevington. So I'm not going to go over it here. And if you plot the Poisson distribution, you get a graph that looks like this. Notice that it looks a lot like the binomial distribution. So you can ask, why do we care about this limit? And the reason we care about this limit is because it's everywhere. Whenever you count statistically independent identical events, you get the Poisson distribution. So for example, the number of raindrops that fall into a bucket during a rainstorm, the number of photons that hit some small square coming from a light. What we investigated was the number of gamma rays that hit our detector from background radiation. And there's one more distribution to consider that we were comparing the Poisson distribution against. This is the Gaussian or the normal distribution. You can get the simplified version of this when you consider the Poisson distribution for large mean, and you get this formula. There's a slightly more general formula when the standard deviation is not equal to the mean. And that's the formula at the top of this graph. This is what the normal distribution looks like when you plot it. Note that it's symmetrical and not necessarily discrete. And so those are the distributions that we need to consider. So for our experiment, we used a scintillation counter to investigate background radiation. And this is how a scintillation counter works. There's gamma rays from background radiation. Hold on. And so there's gamma rays from background radiation. The animation seems to not be working perfectly. And when the ionizing radiation strikes the scintillator, it fluoresces, it emits light. The light goes into the photomultiplier tube, and the photomultiplier tube takes incoming light, and then it sets off a cascade of electrons that are accelerated across a potential difference. As you see in the animation, there's more and more electrons at each step. And so and I believe the voltage divider gives you a reference voltage and also gives you the potential difference to accelerate them across. The scintillation counter will then output a signal that a preamplifier can pick up. The amplifier amplifies it to some degree. The preamplifier amplifies it to some degree. The amplifier amplifies it a bit more, and then it goes into a counter. And the counter has a built-in discriminator that lets us count events or count signals above a certain voltage. And this lets us discriminate on what energy gamma rays we're using, because the higher the energy, the more photons that it'll knock out of the scintillator, and so the larger the resulting signal will be out of the scintillation counter. And So what we did is we looked at the distribution of counts for the mean rate of counts being approximately 1 per second, 4 per second, 10 per second, and 100 per second. And this is what it looks like for 1 per second. We found an average of, unsurprisingly, about 1 per second. This is what we set the discriminator to. If you look at the Poisson and normal distributions, and I did a chi-squared test on them. Chi-squared for Poisson was 3.4, for normal was about 350. P-value of 0.33 is not enough to reject the hypothesis that it's Poisson. A p-value of 10 to the minus 67 is by far enough to reject the hypothesis that it's normal. At like 99.659% or percent confidence that it's not normally distributed. At mu equals 4, we can still reject the normal hypothesis. 10 to the minus 13 is not quite as small as 10 to the minus 67, but it's still pretty small. And again, it's well modeled by Poisson. By mu equals 10, we can only reject it at about the 99% confidence level. But it's still pretty definitively Poisson and not normal. And but when you go to 100, there's practically no difference between fitting into a Poisson curve and fitting into a normal curve. And so you look at our table of chi-squared values and p-values at around, for anything below 10 and also around 10, we can pretty soundly reject the hypothesis that background gamma radiation counts are distributed are normally distributed. These chi-squared values support the hypothesis that they're Poisson distributed. By mu is about 100. There's practically no difference, and so we can't reject either hypothesis. Thank you. Any questions?